Okay, guys. Good morning to everybody. Okay, we're working our way around these alkene reactions. We've done these up to this point here. Cyclopropanes, two different cyclopropanes using carbenes. We're now ready to look at the last two reactions. Both of these reactions we will be forming alcohols. We formed alcohols before by reacting with aqueous acid, H3O+. These will be new ways to make alcohols. Before we get started, any questions about lab this week? Your worksheet for the hydration lab will be due in lab. Worksheet, no report, worksheet. We're doing this week, what are we doing this week in lab? Yes, that's right. Okay. We have our white outline. We'll come back and look at some of those questions that are within this outline, but we need to move ahead. Next reaction, oxymercuration, alkoxymercuration, followed by reduction. Let's look at this reaction. First off, a review. We take this alkene reacting with aqueous acid like we did last week in lab. You get this alcohol here. We've covered this exact reaction before. And we get the oxygen here because of a carbocation rearrangement. Okay, we can envision this attacking, making carbocation here. Then a hydride shift. There's a hydrogen here, can shift over, carbocation here. Water attacks there, and then you lose proton from water. We've already looked at this. Comes from a rearrangement via hydride shift. What if you did not want a hydride shift? What if you wanted the water to add here? Well, you can do that using these conditions. It's a two-step process, the mercury acetate. And the first step is called oxymercuration. And then we come in with sodium borohydride, and this is a reduction. And here we can get an alcohol with no rearrangement. The reactions we're looking at, there's no carbocation. Since there's no carbocation, we would not expect a rearrangement. No rearrangement here. Alcohol. Let's look at this mechanism. I'll leave it like this. Mercury acetate. We can show this sort of partially ionized. I'm not really going to show mechanism, but we can show this as mercury, just one acetate, plus the other acetate sort of separated. What's the charge of acetate? You guys know acetate? Charge of acetate is negative. What's the charge of the mercury here if it's holding one acetate? Yes, positive. If we showed it completely ionized, we would make two acetate anions, and the mercury would be 2+. Okay? We can maybe work with it, mercury 2+, but this is common. But the mercury is electrophilic. We've worked with H+ before, right? Alkene attacks H+, that's the mechanism up here. Well, alkene can also attack mercury+. Where are we going to leave cation? Top or bottom? Bottom. So this pulls away from the bottom and goes attacks the mercury. All right? That's a long mechanism. Arrow, I could have drawn it right here and been a little bit closer, yeah? But when it opens up and attacks, what do we get? Boom, 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 boom. Bonded to mercury, the acetate is there. Sort of covalent or ionic, it doesn't matter. Not really going to show it either. And then what's here? Electrons went out and made bond to mercury. What's here? Carbocation, right? Okay. Importantly, mercury does have at least one lone pair. Since it has at least one lone pair, what do you think is going to happen next? By the way, we have water. Is water going to attack here? Or would something be faster? Back bonding would be faster, yeah? And if it back bonds, what do we get? Boom, 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 boom. Mercury now bonded here as well. The acetate is still there. By the way, what's the charge of mercury here?
2+.
It's neutral. How can you tell? Well, if you agree that it's plus there, it's the same except now it owns one of these electrons. Where here it owned no electrons over here. If it was plus and now it owns one electron more, it's now neutral. When it back bonds, it's now positive again. Because now it owns two electrons. If it's neutral here, it owns both of those. But now that it's bonded, it only owns one of the electrons. So it owns one less than it did here. So if that's neutral, this should be positive. And there you go. There's a bridged mercuronium ion, analogous to a bromonium or a chloronium. So do you think the cation is really an intermediate? No, it is not. It's NaF. Because as soon as the alkene is attacking the mercury and making a bond to the mercury, what's the mercury doing? It's back bonding at the same exact time. All right? It's a concerted process. This is your first intermediate. Of course there's no cation. We're under Roman numeral 2 or B or whatever on the green sheet. Roman numeral 2. These reactions do not involve a carbocation intermediate. It says it right there. There's no carbocation intermediate here. This is just me drawing on the board. You know the story. Here's our first intermediate, mercuronium ion. The water's here. This thing is strange, just like a bromonium. Nucleophile will attack and kick these back off. Is it going to attack the top carbon or bottom carbon? Because we could attack here and kick this bond off, or we could attack here and kick this bond off. Well, the answer is the same as where the cation would have formed. The water attacks here and kicks these electrons back off. Hopefully you got your room below there. I'm going to move up in here so I won't move the text. Let me draw here. Let me draw it over here. Boom, 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 boom. Mercury acetate, but on this carbon, we now have the water, and it's got two H's. One electron left, that's a positive charge. So we get to here. By the way, yes, this is backside. If we had any stereochemistry here. So why am I not showing the oxygen up? Well, you also have free rotation. So if you have free rotation, you draw it however you want. We're not really looking at stereochemistry yet. Even if we were, we could still draw it down if we had the right stereochemistry. The reason I drew it down is because I did a zigzag. If I had put this bond up, that's going to be an ugly bond angle. You know, if I draw all my bond angles like this, it's just going to be ugly. Okay, what can take the H here to go neutral here? Well, there's this acetate floating around, remember? Original acetate. We can use the acetate. Everybody know the structure of acetate? Acetate, right? Should have learned it in Gen Chem. Boom, acetate. If you put an H on here, you have acetic acid. It's the anion of acetic acid, right? These electrons take the H. These electrons move on to oxygen. And we get, boom, boom. Where did that come from? Did I draw this extra?
Yeah.
Yeah. Yeah, it should be. Boom, boom, boom. And then right here we have this OH. Hopefully you got some room here. What did we make? We made acetic acid, ACOH. That's abbreviation for acetic acid. This is ACO, because this here is an acyl group. Carbonyl methyl is an acyl. So this is ACOO minus. ACOO minus. If you put an H on the ACOO, ACOOH, that's acetic acid. That's in step 1. Hopefully you can see here, okay? In step 1. Everybody can see? I doubt you can see that. That's in step 1. What have we done to the alkene to get here? We've added in mercury, and we also added water with loss of protons. Or you could say this, we've added an oxygen to one carbon and mercury to the other. Oxymercuration. Oxymercuration of the alkene is what we just did. You can also use an alcohol here, or alcohol. If you use an alcohol, which is ROH, this would be an OR after you lose an H. And if it's an OR, we can call it an alkoxymercuration. That'd be an alkoxy and that'd be a mercury. So this is the first step, either this or this. The second step is a reduction. Reduction is done by sodium borohydride. What do we need to do to get from here to here? What do we need to do to get home? We have to remove something, obviously. What do we have to remove? The mercury from this carbon. How many H's on that carbon? 3. How many H's on this carbon? Only 2. It's the same number as we started with. There's 2 H's there, and there's 2 H's there, there's 2 H's there. There's still only 2 H's there. We have to replace the mercury acetate with what? A hydrogen. Where does that hydrogen come from? Sodium borohydride. Sodium borohydride we'll see here. You'll see it a good bit in organic too. It's a boron with 4 H's. What's the charge of the boron? Well, it owns 4 electrons. It owns 1 of each bond, 4 electrons. It's only supposed to own 3, so the charge is negative. And so you can have a cation with it, It can be lithium, potassium. Very common is sodium. And this is sodium borohydride. It is a source of H minus. H with a lone pair would be minus. What do we call a hydrogen that's minus? Hydride. Just like you call a chlorine that's minus chloride. The source of H minus. How is it a source of H minus? Well, boron is hard to please. Okay? It's either neutral and doesn't have an octet, wah, wah, or it's an anion, wah, wah. Okay? You can never make boron happy. In this state, it doesn't like being minus. So it says, okay, hydrogen, you need to split and take the electrons with you. And if we can just envision this just leaving, it'll leave and become what? If the H and 2 electrons leave, what does it become? It becomes H minus, H and 2 electrons. We can even just say it becomes this plus what? What does the boron then become? It would then only have 3 H's. And what's the charge of the boron now? It's now neutral. This reagent sort of shoots these H minuses off like darts. Okay? Boron doesn't like this extra H there, so it shoots it off, if you want to accept that shooting off language. Now boron's not happy again because now it doesn't have an octet, so now it wants to go back. Again, you can never make boron happy. But you'll see this reagents like this in organic 2. We have H minus. I'll just use that. A lot of times you just use that in the mechanism. Okay, I'm going to show you a mechanism that's not correct, but the true mechanism is too convoluted. Let's do it like this instead. Got H minus, okay? Let's just say it came from there. We can just use this. These electrons add here and kick off the mercury. The mercury is going to be a leading group. What would this give? Well, we give this because now we have the H there instead of the mercury. But again, this is probably not the mechanism. The mechanism probably involves the H maybe interacting with the mercury, or it may be a radical. But I'm going to show you like this because this is going to be more useful going forward. Everybody see? Doesn't that give this product? We're home. There we go. It's a 2-step process to give this product. But let's keep track of the mercury. What does the mercury become? Well, it's now gone. It's mercury acetate. But what does this arrow mean? What's on the mercury now as a result of that arrow? A lone pair. What's the charge of the mercury thus now? It's neutral here, right? What is it now? Negative now, right? Because if you look at these electrons over here, of the 2 electrons, mercury owns one of them, because it owns one of each bond, owns one of those electrons, but now mercury owns both of them. So it owns one more than it did there. If that's neutral, this should be minus. We already made this product. Let's keep track of this, though. Mercury doesn't like being minus too much. It tends to be a metal. I know I'm writing all up here. Hopefully you got room down there. From here, the acetate can just leave. If we form acetate minus, what would be the charge of the mercury? And is it this sort of ionized? And the mercury would now be neutral. That would be elemental neutral mercury. It has lone pair, but just mercury metal. Like in your thermometer. The mercury metal is an environmental hazard. Because this reaction produces mercury metal, it's not used much in industry. Industry doesn't want to produce mercury. So it's today more of a textbook reaction, but it's very important mechanistically. Okay, some terminology. We do need to understand Markovnikov. I don't like to use that term to predict mechanisms. Markovnikov is an alkene reaction that gives a standard product based on mechanistic theory we've been talking about. Where would you make cation? Here. And thus, water attacks there and you end up with oxygen there. Assuming you don't have a rearrangement. That's a Markovnikov product. All the reactions we've been doing are Markovnikov products. Nucleophile ends up where cation would be. That's a rearranged product. Standard Markovnikov product. Without rearrangement. That's what this process of oxymercuration followed by reduction. By the way, when you add H's to a compound, that's typically a reduction in organic chemistry. If you remove H's from a compound, that's typically an oxidation. That's one way to keep track of redox in organic chemistry, because typically it's not done by looking at oxidation states like you do in Gen Chem. So this is a reducing agent. It adds H's to things. It's a hydride source. Questions while I'm erasing? I sent out a puzzle worksheet on Friday. Everybody get that? It's a very good worksheet. A little puzzle. How is the alkene able to learn all of its electrophilic reactions? And you get the answer to the puzzle by filling in the products to each reaction. Let's look at this reaction down here. Same alkene. We'll do this reaction. Here, the oxygen from the water ends up on the N carbon. So let's just think carbocation. If we made carbocation, where would we make it at? Top or bottom? Bottom. And then we can envision water adding there. A good old classical hydration reaction. So oxygen would be bonded there. And that would be the standard outcome, called Markovnikov outcome. Markovnikov was a Russian chemist in the late 1800s. We'll learn about his colleague Sesev a little bit later in the course. Oxygen here would be the standard product, Markovnikov product. Getting the oxygen out here is called the non-Markovnikov product, or sometimes the anti-Markovnikov product. Like, how did you get the oxygen out there? Carbocation would be here, water adding here. It's an unusual non-Markovnikov product. You can get such a product by this process, hydroboration followed by oxidation. we see our friend BH3, which is not happy, followed by oxidation of hydrogen peroxide. By the way, BH3, because it's not happy, it actually exists as a dimer. It's a very unique structure where hydrogen's making more than one bond. Or is it really? Kind of is. Anytime you see this, just consider it BH3. That's just a dimer of BH3. You may also see some other borane reagents. They all act as if they're BH3. How can this react with BH3? Well, what type of reactivity does BH3 have? The H's are not acidic. It's not a Bronsted-Lowry acid. Let's focus on the boron. Does it have an octet? No, only 6 electrons. Okay? Since it doesn't have an octet, it would like to have electrons. And something that likes electrons, we call it electrophilic. And the pi electrons would be attracted to this because this has an empty p orbital. Because if you graphed it, it would be sp2, 3 hybrids, and an empty p orbital. These pi electrons are attracted into that empty p orbital. This thing thus accepts electrons. And what do you call something that accepts electrons? You can call it that. What else? What do you call it in Gen Chem? Yes, a Lewis acid. What's the definition of a Lewis acid? Accepts electron pair, right? Yes, it's a Lewis acid. Okay? By the way, H plus is a Lewis acid. Mercury acetate's a Lewis acid. A lot of things have been accepting electrons. Anything that's attached is a Lewis acid. But specifically, it's a Lewis acid because it has an empty p orbital. There's no charge here. It's not a plus boron. So why is it being attacked? Because it has an empty orbital. I'm going to draw the BH3 here. So you got to understand the reactivity here. Even though there's no charge, it's still electrophilic. These electrons attack. Where are we going to leave cation, top or bottom? Top carbon bonded to H. I'm sorry, to boron, 3 H's, and this would be a carbocation. This swings out, makes bond to boron, leaving this without a bond, carbocation. What's the charge of the boron now? It's now negative. Okay, we showed a cation. But you clearly know there's no cation in this reaction, right? We are under Roman numeral 2. So what gives? In the past, we've had lone pairs over here. There's no lone pair. So what can happen here? Well, here's a little twist. Remember that boron? It's never happy. Why is it not happy now? Because it's negative. What could this boron do? What did it do when it was like this? It shot off a hydride. Well, this shoots off a hydride because now it's in the minus state again. What happens here is a hydride shift, and we've done that before, except it was next door. If that's 1, 2, 3, this hydride comes in over here. The electrons breaks away, or you can say the boron shoots one of the hydrides at the cation. The very top reaction involved a hydride shift if you look back when we did it. Except that one was a 1,2 hydride shift. The hydrogen was transferred to the next door carbon. Here the hydrogen is not transferred to the next carbon, but the other one. So it's a 1,3. So we do a 1,3 hydride shift. And what does that give? Boom, 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 boom. Gives a B. Only 2 H's on the boron. What's now on this carbon? It was not over here. That H, I'll draw in the H. And that's it. This carbon is now neutral. You gotta know how many H's are there. How many total H's are on this carbon? 2. How many H's on the carbon there? 1. How many there? 1 H there, 1 H there. But when this one comes over, there's now how many there? There's now 2 there. There's now 2 there. I only drew in the new one. But that's why it's neutral, because it has 4 bonds. There's 2 H's there. So, the important thing is, this cation is not actually formed. Because as soon as this attacks the boron, as soon as this bond is being formed, the hydride is being shifted over at the same exact time. So it's only one transition state. All right? I'm attacking you, and as soon as I attack you, you throw the H. You got to be throwing it as soon as I come. It makes the sound. Okay? Boom. As soon as I attack you, you're throwing in the H. One transition state. Only, there's no intermediate. It's directly here. Not actually formed. This is it. And by the way, this is in step 1. What have we done to the alkene? We hydroborated it. We did a hydroboration. A hydroboration across the pi bond. We added BH3 across the pi bond. The 1 H is here, and the other one's a BH2. What's the charge of that boron? Neutral. That's in step 1. That can be isolated. Because when we do 1, 2, a lot of you guys think all this is together. No. Like we said when we looked at line reactions, this is the first step. You can isolate this. Sometimes it's probably difficult, sometimes you don't. Then you come in with the second step. Then we come in with this. What do we need to do to get the final product? There's 2 H's here. We've got the H's there. What do we need to do, though? We haven't got the oxygen on there yet. We've got to replace the boron with what? Replace the BH2 with the OH. That's what we still need to do. Because if you look at this, 1 H here, 2 here. Well, we got the 2 there, the 2 H's there, but we ain't done anything over here in terms of getting an oxygen there. Okay? Well, this is this, okay? Reaction number 2. Hydrogen peroxide and base, aqueous base, like KOH or sodium hydroxide. This is oxidation. Hydrogen peroxide is typically an oxidant. We're not going to look at the mechanism here. The mechanism is magic. Those reagents replace the boron with the OH. Not going to be looking at mechanism. It's a little bit too convoluted and not long-term useful. Importantly though, no change in stereochem. Once we start doing stereochemistry here, if we have stereochemistry, we just erase and put OH. No change in stereochemistry. We'll be doing that down the road. And if we magically replace the boron with an OH, what do we end up with? There's your product. What have we ultimately done? We took this alkene and we added H2O to it. Because we added an H there, H2O. We hydrated the alkene with this crazy set of reagents. Now we say we hydrated it, we added water, but that's just formally what we've done. There's no water here at all. Well, that's probably aqueous. But when we say we add water, that's just like looking at the formula. The formula now has water added to it. This product is called a non-Markovnikov product because we're like, well, how the heck did the oxygen end up out there? Based on carbocations, it should be here, like oxymercuration gives. Hydroboration oxidation gives a non-Markovnikov alcohol product. The oxygen, the water ends up on the carbon where you would not expect the carbocation. All right, let's see how we do down here. First reaction. Just like with all reactions we do, you first need to say, okay, what's going on? We got an alkene. Ah, that looks like hydroboration oxidation. What does that do to an alkene? Anti-Markovnikov alcohol or hydration. So all that right there is really memorization to get you going. Back of a note card. That's what. So you have to assess what's going on. This is an alkene, hydration, anti-Markovnikov. We could go through the mechanism, but is the OH going to end up on top or bottom? The OH, when we're done. It's going to be on the bottom. That would be anti-Markovnikov. Now cation, if we want to think about where cation would form, cation would be on top or bottom? Top. And then if you added water, but that would be a standard product, like a H3O plus product, or an oxymercuration product. This gives the opposite. The OH is going to be on the bottom. And so we would get methyl at top and OH on bottom, and there's your product. We added water across the pi bond. There's the OH. Where's the H at? Because you got to have two H's to have water, H2O. Where's the new H? The new H is up there. Isn't there an H there? Yeah. There's a new H there. Where there was no H. So we've added two hydrogens and an oxygen. That's H2O. There's your product. But what about stereochemistry? Are these two groups cis or trans? That's a nice six-membered ring. We know that things can be cis or trans coming off the ring. Are they going to be cis or trans? Cis or trans? Cis or trans? Let's go through the mechanism, see if we can answer that by knowing mechanism. Cis or trans? Okay, mechanism. This attacks boron. Okay, we can pull it down here. We're going to leave cation on top or bottom? Top. So this pulls away, attacks boron. BH, H minus. Cation up here. Importantly, though, this down here is now tetrahedral because now we have 4 bonds. So this is going to either be forward or back. Which one do you want to make it, or either? Be forward or back. Let's make it forward. Or it could be back. Because the alkene attacks, but the boron could be on this side and attacks forward, the bond is forward. Or maybe you're over here and I attack this way and the bond would be back. 50-50 chance. Okay? But if it's forward, and then this throws the H, by the way, when you look in the book, they're not going to do it like I do. They're going to show you just a transition state. They're going to talk about how the transition state has more partial positive here and all this. If you want to do it that way, fine. I base everything on where's cation going to be? And then go from there. But then I have to tell you and warn you, hey, it's really not a cation in many cases. NAF. But this gets thrown in, right? Boom, a 1,3 hydride shift. But here's the important question, $1,000,000 question. When we put the new H here, is it going to be forward or back? It's going to be forward unless you're throwing curveballs. Okay? I bond it to you, and let's do a cation. Not really a cation, let's do it anyway. Now you throw an H, you make a bond, throw an H, throw your pen there. Throw an H, make a bond, keep it in your hand. Make a bond. Boom! Okay? But that bond's also coming forward. It has to be because it came from you. Unless you want to throw me a curveball and come in back over here. It's got to be forward because if you're forward and you make a bond, act like it's a dart and it sticks. Throw it. Boop! And it's stuck. Bond to you is that way. That bond's forward also because it came from you. Okay? If this is forward, that's going to give this is forward. It's now a BH2 though. I'll show it condensed. The new H though is also forward. The methyl gets pushed back. This is now tetrahedral. Okay? These two groups, this is in step 1, remember? The BH2 and the H. Did we say in step 1 up there? Didn't it have the BH2 and the H? A hydroboration. But these two groups are in what? Are they cis or trans? They're cis. That's also called syn. Those two groups are syn, which is the same for us as cis. Syn means same side. They have to be because the H comes from the boron. Pushes that back. Now the magic step. What does the magic step do? It replaces the boron with what? An OH. So when we replace it, do we change any stereochemistry? No change in stereochemistry. Exclamation point. So just erase and change it to OH. No change in anything. The methyl group is up here. Like that. And what do you say we don't draw in the H? Starting on day 1, we have rarely drawn in H's. Can we just call that the product? Let me ask you again. Is the product cis or trans? It's trans. You see how the groups are trans? If we drew the H here, the H and the OH are cis. That H is there, and it's cis. But when we talk about cis or trans, we're not talking about H's, we're talking about substituents. The substituents are trans. But you're also going to get this product. What's that? But that's also trans. And these two are mirror images. These two are enantiomers. Okay? How do you get the enantiomer? That's where you do everything backwards. Instead of this attacking boron forward, it attacks back. So this would be dashed. And if that's back, the new H up here would also have to be back, because it came from the boron that was back. And if the H came in from the back, it would push the methyl forward. Everything's just reversed. It's the same chemistry, it's just all reversed in terms of your stereochemistry, but that's also trans. Those are enantiomers. We'll start learning about that as we move forward. Finish up the one below. What are we doing down there? Somebody already have the product? Is that one? Alkene. What type of reaction are we doing here? What is this? That's a Markovnikov hydration with no rearrangement, right? What are we going to get? This looks weird when I draw it. Connect. Just that, right? The OH would be up here where you would make cation. But there's no carbocation involved in this mechanism, right? And that's not chiral. So no enantiomer. If you want to have that for your notes later. It's not a chiral product, so there's nothing to show. That's just like if I showed you a paper clip and there's no alternative. The other paper clip's the same. But if I showed you a hand, well, I could also maybe show you another type of hand. These would be enantiomers. This has no enantiomer. We'll be talking about that very soon. In fact, that's about where we're ready to move on to. A few miscellaneous things here. Please take a look. This is the type of stuff for your information if you're interested in the applications. We don't always have time to go over it. Here's an example procedure for an oxymercuration reduction. Organic syntheses. Free to anybody, wherever you're at. Used to not be free. 10 years ago, it used to be by subscription only, but now it's free. Great resource to find reactions, any type of reactions. Over here is a synthesis of a vitamin D3 type analog. Lots of multi-step synthesis. Look what they're doing here, going from 7 to 8. They're using a boron reagent called 9BBN. Anytime we see something like that, boron reagent, just act like it's BH3. BH3 followed by a magic step. Take a look at what they're doing. Did they get the right product based on what we talked about or not? There's other stuff in here. Here they're doing some reaction optimization using BH3 or 9BBN, different temperatures. Most of this stuff is, I know some of you stop by and talk about it. I don't have time to always talk about it here, but it's stuff that you want more information about, to expand your horizons, etc. We'll look at some other miscellaneous things. One last topic in this handout, we need to look at hydrogenation. Green sheet. That would be letter C. Okay, we need to take a look at that. As we exit, I'll call the Friday lab reports one more time since I started early. Have a good day, guys.